We are starting 3.2 today. Polynomials. Alright, let's start with the word poly. What's poly means? Many. Many. So you expect to see many of some certain type of things. Many of what? You expect to see in these expressions many x's with several powers around them. So this looks like a very fancy, confusing explanation, definition, but no. Polynomials are actually very simple things. They are just many powers of x's with just numbers around them. You expect to see numbers before them. It can be negative numbers, positive numbers, according to the sign of the number. It can be addition or subtraction. Okay? Well, when I say just exponents of x, powers of x, technically we don't take any kind of power. We allow only whole numbers. So those powers here should be whole numbers. No partial numbers are allowed, like 1 over 2. Square root x means x to the 1 over 2. This is no good. No partial powers. No powers which are negative. 3 over x means 3x to the minus 1. No negative powers. And the numbers in front can be decimals, fractions, but no complex numbers. Such as 3 plus 2i is a complex number, which is not allowed. So these numbers in front can be pretty wild. Decimals, fractions, square roots are fine, but no complex numbers. And the number on the exponents must be positive whole numbers. That's it. That's what we call polynomials. It looks like in the definition, these powers should go one by one decreasing, like 4, 3, 2, 1, 0. No, that's not necessary. You can skip some numbers, like 5, 4, 3 skipped, you skip the 2, okay? So you can skip numbers, then some of them may disappear. The last number, if there is a number, may not have any x. It's called constant term of the polynomial. Okay? And the biggest number you see in the exponent, this is 5 for example, is called the degree of the polynomial. So this is a polynomial of degree of 5. Okay? It's 5 the biggest. Any questions so far? Is it clear what polynomials means? Just many of x's with raised to powers. That's it. Added or subtract. Okay, first thing we're going to take a look at is basic graphs of very basic polynomials. Technically, if you have only a single term, we call it monomial. So we will take a look at some basic monomials graph in this slide. Here is a monomial. X squared, x to the 4th, x to the 6th. They are graphed with different colors. I want you to observe some general patterns so you can predict the graph of x to the 8, 10, 12, 14 as you wish. Okay? All these graphs are basically U-shaped. U-shaped, right? But the bigger the power is, 4, 6, 8, the sharper your branch is going up, or steeper. Right? Steep angle, they're rising. So the slowest here is x squared. It takes time to rise. And then larger and larger. The more the number is, the closer your branch to y-axis. Okay? That's first. Secondly, it's barely visible on this part. However, the bigger the number, the flatter. It goes really flat in this area if you have bigger and bigger numbers. Look, blue one is on the top, red one is the second, and the green one is the closest to x-axis. Where does it happen? On the base, between -1 and 1 actually, between -1 and 1. Okay? Like cereal bowl, they get much better. It looks like a pot. rather than regular parabola shape. These are one thing common between these numbers, 2, 4, 6. These numbers are called, what kind of numbers are they? 2, 4, 6, 8, 10? Even. If you have an even number, you have a U shape. But if you have an odd number, first, third, fifth, seventh power, you have a side on the left which is going down, okay? Like an inverted S. Look like an S shape but inverted, except the first one. First one is a line, straight line, okay? So the bigger the power is again, you're rising faster and faster, and you're flatter on this area if big numbers, okay? The only difference is it's like a U shape again. Somebody took this part upside down and inverted it, make it upside down. Very similar shapes. Okay, where are we going to use these? These basic shapes, please keep in mind these 3, 5th, 7th, square, 4th, 6th. These will be used to graph general polynomials. These are some basic ones, but more generally, if I add more terms to these, how do we graph them? Eventually we will do it maybe today, maybe next time. But these will be our predictors on the end parts. So your polynomials will act like these on the end parts. It's called end behavior. That's what we are going to take a look at first. So you have a bunch of x's added in a function, in a polynomial, bunch of powers, such as the question 1, x to the 4th, x squared, 8x, and minus. This is a real polynomial now. But my question is, it's going to be going up and down in the middle. How is it going to look like on the far end parts? Far end parts means all the way on this side and on that side. Far ends means end of x-axis, left end and right end. There are 4 scenarios, options can happen. Either both ends go up, both ends go down, left down, right up, right down. 4 cases. Okay? Just like these pictures. Both ends going up, these are going down, going up. Sometimes one part goes up, one part goes down. If I put a minus in front of the green one, then it reflects along x-axis and makes this picture left side going up, right side going down. So imagine you have minuses. These will flip up and down. You may have arms going up and down. There are 4 cases can happen. So in any case, what we are saying is the shape of a polynomial on the far ends are determined by the very first term. In other words, the term with the highest exponent, biggest exponent, determines the ends of the polynomial. So when you're sketching a polynomial, eventually at the end of this homework assignment, there is one problem. You will first make the ends of the polynomial graph. Then we will fill out what's happening in the middle. And the end is found by the very first term. How? This is how. You will first decide what kind of exponent do you have here. Even or odd. Once you find out it's whether even or odd, we decide whether an first number is positive or negative. If it is odd, you decide first number is positive or negative. If it is positive, it will be going both ends up. Negative, it will be going both ends down. Positive, odd, positive, one left side down, right side up. Negative, left side up, right side down. You may feel like, oh my God, how am I supposed to put this in my mind? You don't have to. This is the table. When you hesitate, you refer to. But technically, if you already know these basic shapes, which I'm going to I assume you know, right? It's not too hard. Even numbers are U-shaped, odd numbers are inverted S. If you know these shapes, you can make this table on your own. I will show you how on this problem, okay? But again, to double check, always my guess is right or wrong, I will go back and use this table anyways. For insurance, you can keep it on the side. Okay, here's our question. It says determine the end behavior. We are not supposed to graph entire polynomial, we will just figure out the end of it. So why don't we choose our x and y axis here. Okay. And end behavior is determined by the term with the biggest exponent. Which term has the biggest exponent here? Not these, but this one. Now, at this stage, you can refer to this table and apply the directions here, but no, I'm not going to do that. Here is what I'm going to do. First, forget about the number in front. Just take a look at x to the 4th. And graph x to the 4th here. What kind of shape can it have? Either U or inverted S. Which one? U. This is a U shape. So sketch a U shape, x to the 4, but it's flatter and faster. So it's fast and it's much more flat in this area than x squared. Okay. And what do? I go ahead and incorporate what this number does to x to the 4th. When I take a negative, what happens to the functions? When I put a negative in front of a main function, a graph of a function, what kind of shift or change happen? Yes, negative sign in front of a function. If you have a formula like x squared, x to the 4th, this negative means reflection across x-axis. So we are going to make this picture upside down. So let's do it. This is negative x to the 4th now. Later, remember what 3 does. When you multiply a function by 3 in front from transformation of graphs, 2.6, what happens? When you multiply a number, what happens? 2 options, shrink or stretch. It gets closer to y, it's stretch. If the number is more than 1. 3 is more than 1. I will just modify this. And it's going to be a lot flatter on this area though. Okay. Alright. So what I did here is I drafted picture of negative 3x to the 4th. But what do I do? This is not, again, the graph of the entire polynomial. Only the leading term graph is this. And we know that the leading term decides the end behavior, how this polynomial is going to act like on the far end and far left end and far right end. So all you need to do is delete the part in the middle, okay? And only leave the ends, end of those 2 branches. So what kind of pattern do you see? On the left end, my function is going down. On the right end, my function is going down as well. So we got this situation. Which one? This one. Is it really true? Yes, n is even here. And the number is negative in front. So, well, my prediction is right. It's verified by the table as well. the left side and right side goes all the way down. However, this is not what you're going to picture. It's not what you're going to picture in the homework. They don't want any picture like this. What they want is you need to fill out this table. So I'm going to explain what this notation means. X going to minus infinity means minus infinity is, just imagine, negative huge number. A number you can't count, it's so huge. So what side do we describe on x-axis then? By saying this, x is getting closer to obtaining huge values. This arrow means getting huge values, negative huge values. So which side of x-axis? This is x. X values are here, 1, 2, 3, 100. Negative 1, negative, then 1, negative 100. So which side is it describing? The left side. So this means, in English, this is mathematical, far left. So it says on far left side, what happens to function values? Where does the function values go? Okay, I see far left, this is left side, and this is as far as I can go on the graph, and I see really some values like this. And what kind of values are these? What is on this end? Minus 10, minus 100, minus 1000, but this end is f of x. What kind of values here? Negative huge. How do you write huge in math? Infinity. So it is negative infinity. On the far right end, this means positive huge. Positive huge. This means far right. On the far right here, on this side, on this, imagine this arrow goes down, and it opens to that side to the right as well. What kind of values f of x gets as well? Negative huge or infinity. Okay? This is what you're just going to supply in the homework. Alright, that's not your homework. Why don't you guys take a look at the second question while I'm fixing my homework, okay? Take a look at a similar question. Alright. Negative infinity is what the answer was for this question. Both ends going down means both ends are going to negative huge values. Now, what do you think about number 2? Oh, this is easy. All I need is find the biggest exponent, right? This is again the biggest exponent. Oh, what a coincidence. It's the same as the before. Negative 3x to the 4, same, right? So can I just cheat and say negative infinity and negative infinity, just cheat from the first problem? Not so fast. Not so fast, because this is incorrect. This is not the leading term. Yeah, it's the first term you see and biggest number you see around x. However, it's not the leading term. Leading term is obtained once you perform all your products. Like I can take an example here. Alright, this is the leading term for this polynomial, but when I convert this back to factored form, is this guy the leading term just because it's in front? No. You need to FOIL this, FOIL it, and get this equation and determine its leading term. So it looks like we need to FOIL, multiply out all this mess. Can you expand 3 minus x cubed How long is it gonna take? 3 minus x cubed means triple 3 minus x. Wow, it's gonna take all afternoon. You're staying here. Right, I need to expand that. No, you don't have to do that. All I need is to figure out what is the best, biggest x and power I can get from this expansion. Can you predict it? Predict it. It's minus x times minus x will multiply and make plus x squared. Imagine you FOIL this, I get plus x squared, and then another minus x will come later and multiply this, and I will get minus x cubed out of this mess, and then yeah, you will have a bunch of other things. So all you need is ignore the numbers. Okay? Only consider when you raise this expression into cube, what happens to x values? This will be, first one will be still minus 3x to the fourth. The second one will be minus x cubed. The last one will be 2x. And multiply these out now. By the way, minus x cubed is the same as, you can pull this minus in front and combine with this, and becomes positive 3 and 2 times 6. Positive 6. X to the 4, x cubed, and x to the 1 combines into what? Cube fourth power, 4, 3, 1 more. You get how many x's in total? X to the 8, right? So there you go. You found in 10 seconds max what will be the leading term of this expansion without doing any expansion, without doing this work. Okay? So I'm going to go ahead and say here, when I expand this, guys, first term will be 6x to the 8, and then yeah, we will have a bunch of other things which we do not care because they will be less and less power. 7, 6, 5, etc. Did you get it how I got it? All I did was multiply these numbers first. 2 negative and negative made 6, positive 6, and add up the powers, cube and fourth power. Okay, now you can describe me the end behavior. This is an even number. 6 is going to just make it sharper or steeper. And this is positive, means regular direction of x to the 8. It's not upside down. So what does x to the 8 look like? It's not here, but I bet it's going to be somewhere like this. It's going both ends up. Both ends are going up. That means the answer is this function will be going on the far left side to, if it's going up and up and up, positive infinity. On the right side it is positive infinity as well. Correct? Because that's how x to the 8 behaves. Both ends infinity. Agree? Is it clear? I just want to make sure. Okay. Again, don't go with trial and error. Don't choose every other option here. Okay? First, see what's going to happen, and then put in your answer. Don't do trial and error. Alright. End behavior is over, but that doesn't mean we won't be seeing again. We will see it soon again. But we need to first talk about zeros. Okay? Finding zeros and multiplicities, determining their multiplicities. What is the meaning of a zero? When I say zero, most people think, oh, we need to substitute 0 in x. they start substituting zeros in x because its name is 0. No, we don't mean the digit 0 when I say 0. Zeros of a polynomial or function means any other number, it can be any number, other number, that you set it up, you substitute in x, the entire expression becomes 0. So the result is 0. So it's a zero maker. A number, a random number, you insert into the function, and it makes the whole thing 0. Okay? Alright. Why zeros are so significant? Since they make the y value 0, right? When you enter a value and g of x becomes 0, it's y value. When y value is 0, that means that point is on x-axis. So I know the graph crosses my x-axis at zeros. So zeros, and other name for zeros, visual name for zeros is x-intercepts. Okay? So when you actually have been founding zeros of polynomials before, last class, for example, we described x-intercepts. We found x-intercepts, right? By setting y into 0, you were finding zeros back then. It's not something new, it's just a new terminology. I asked you to find zeros of, what was the previous question yesterday? We found zeros of a polynomial. Which one was it? For example, I can make a new one. Quadratic function, right? Yesterday. I asked you to find x-intercepts of this function. What did you do? You set this up into 0, because that's y value, right? This is f of x. You set y values into 0. And afterwards, our first step is always to factor it. We try to factor, and this is x minus 3, x plus 1. And in that factor, you take each piece and left axis alone. And we call these x-intercepts. I want you to call, in this section, these things as zeros of the polynomial. Let's call it a name, p of x. Okay? Zeros of p. That's what we are going to do. However, problem is, before this class, the worst polynomial you've seen was degree 2. We call this quadratic equations, square equations. In this class, in this section, we may have ugly polynomials like cubes, 7, squares. Okay? Now, how can I find zeros of them? It's all about factoring. If you factor them and set each into 0, this one to 0 and that one to 0, you already find zeros actually when you factor them. All you need to do is wipe off these powers, because you don't really need them. Because 7th power of something 0, then that base is 0. So you wipe off the powers first and take the number to the other side. There is nothing to take the other side, so this is already the answer. You have x equal 2, x equal negative 4, and x equals 0, you have 3 zeros. 0, 2, and negative 4. Okay? But what happened to those powers? They mean nothing to us. They're just numbers. They're on the factors? No. They are called multiplicity. Look, you have a 2 here, multiplicity 2, 3 here, 3, and 7 here. That means these factors, x plus 4 shows up 7 times in that expression. Okay? 7 times. It's kind of a strength of a 0. Okay? So they will be used in graphing. I will explain how they make a great impact in graphing. Right now they don't mean nothing. Okay, they're all 0 makers. You substitute them and you get the 0 in the end. They just show up these numbers on the powers. But they are useful when you're graphing polynomials. We will talk about it. Okay? Now, although this is a big degree polynomial, 7, 3, and square involved, this is easy operation. This is an easy question to find zeros. All you do is set into factors. Here it's not so easy. This is not so easy. Why? What do you see different here? It's not as big as this power. We have 7th power here. This is cube, square, and etc. Why is this not so easy? It's what? Odd number? Okay. I don't mind odd numbers actually. They're okay. It's actually, what is the difference in their appearance? What do you have here?
Those are being multiplied and the bottom one's being added.
Right. This is called, when you turn things into multiplication, this is called factored form. This has already been factored for you. Somebody did the hard work and factored it for you. Do you see multiplication among group of parentheses blocks? No. This is a regular standard form of a polynomial. You need to first factor this to find out their zeros. So you need to work this out. Okay? How do I factor a cube expression? This is not just any cube expression. This is actually a suitable one. Somebody set it up nicely for you. How many terms do you see? 1, 2, 3, 4. In 1075, or a class before this, high school, have you guys seen factoring by grouping? Grouping method by factoring? Usually, once you're given a string of numbers or expressions, you look for something common in all 4. There are 4 different personalities here. Do you think something can common in these 4 individuals? Anything common in 4 of them? All 4? Maybe there is. Do you see any? This one has X, this one has X, this one has X. Unfortunately, the last one doesn't have one. I wish there was an X here. It doesn't. So this one is a deal breaker. Oh, this one has 4, 4, and 16. I can pull a 4. But this one doesn't have a 4. So always there is a bad guy ruining the group experience, right? They don't have something come up. So if 4 people go out and you decide to go to movie and you can't come up with a title, what do? There is always somebody who says, no, I don't want to go to that movie. What do? You're 4 friends, and nobody can agree on a single title. What do?
Split up.
Yeah, you split up. You go, 2 people go their own way, the other 2 will go to another movie, right? Correct? So why don't you take a new look at now? Do you see anything common between these 2 guys? Yeah, I have plenty of x's common. So can I borrow 1x squared from each? When I remove x squared from x cubed, what is left? If I remove x squared from this, there is still 1x left, correct? When I remove x squared from this guy, what is left? Okay, this is fine. How about this group? Anything common between these 2 guys? They're going for another movie. -4, yeah. Now look at this, what a coincidence. How lucky you are. When you remove minus m4 from this guy, what is left? X only. When I remove one of the 4s and one of the minuses out, what is left? +4. Do you see something coinciding? Do you see something that's not luck? Somebody arranged this thing. Do you see anything here? X plus 4s. They have typed in this question so that these two can match. Usually this doesn't happen in any cube expansion like this. They have put 4 terms and you group them nicely. These two match. Now all you need to do is factor these again, call them out here, call here as x plus 4, and remove these, literally, take these away. You took them away to here. What is left in those groups? Left group, x squared, you have a minus, and 4 left. Look at this. You have factored it, but you can do better. This is okay factoring. You can do perfect factoring. What else can you do here? There is one more thing you can do. Just look for further factorization. Can you break x and 4 more? X plus 4 more. Walter?
Can't remember. Came back, like you can break the s squared minus 4, like you can times it by s, like s, I think s, x minus 2 and s plus 2.
There you go. It's called difference of squares. If you have two numbers squared and a minus in between, that can be factored as, you repeat those again, AB, AB. Once use a plus, once use a minus. Now how is this related to that? I see x squared, right? Just x is different, a is x. Well, where is the square on this one? It's 4, right? It doesn't have a square. Yeah, it is actually a square, 2 squared. So squares are already matching. All you need to do is make a and b x and 2 here. So x plus 2, x minus 2. There you go. You broke this all the way to the end. Okay? Mission accomplished. Now you need to determine the zeros. What makes this expression 0? So you want this to be 0, and literally set it into 0. Take really each part apart and see what makes each part 0. Set each part into 0. And you find -4, -2, and 2. You're done. How can I test these are the right or maybe wrong answers? How can you test this? Take each and plug it in here and see if they really make 0. That's the meaning of a 0. You enter them into x in the expression and see if they make 0. Once you enter it, they should, unless we have messed up on the grouping part. Okay? So what lesson have we got here? To find zeros of the polynomials, you need to factor them and set each part into 0 and count multiplicities. Multiplicities means how many times these factors showed up, what powers each factor possess. What is it? each shows up once, so each 0 has multiplicity 1. So we have obtained 3 different zeros, and they were -2, -4, and 2. And each has single multiplicity. Okay? Is it clear?
How does the multiplicity work? Like, why is it only 1?
Say it again.
Why is the multiplicity only 1?
Because in the factorization, how many x plus 4s do you have in these factors? 1x plus 4, 1x plus 2, 1x minus 2. Sometimes this may happen, such as this could have been x squared minus 4x plus 4, and when you factor this, you get x minus 2 squared. So you have x plus 4, x minus 2, but this one is a square. You have only two zeros, but this one is double strength. It's double repeated. So this has multiplicity 2, okay? So if same factors show up like this, you need to collect them under the same base, under the same exponent. So one here makes 2, and this is called multiplicity. If there are repeating factors, that repetition amount is called multiplicity. Okay? Alright. We are skipping to number 6 because in number 4 and number 5, all you need to do is same thing. Okay, we can do this question right on the screen. For example, number 5. Why? Why this question is ready to be answered? Why? Don't we need to factor this? It's already been factored. All you need to do is count how many different factors we have, set each into 0. So I have x to the 4th here. That means x only. This is x plus 1, x minus 2. I have 3 different zeros. X plus 1, and x minus 3 will create 3 different zeros. When you set x into 0, you get 0. When you set x plus 1 into 0, what do you get? -1. When you set x minus 2 into 0, you get 2. In short, we always take opposite of these numbers showing up in parentheses. Plus 1 gives us -1, minus 2 gives us plus 2. Well, where is the number under 4? It's actually x minus 0. If you want to make a number visible next to x, it's x minus 0 raised to the power 0. So 0 is the 0, okay? Or how about the multiplicities? 0 came from this factor, and it has a power 4. That means x. That factor shows up 4 times. So it has multiplicity 4. -1, 2. You just count the numbers in the exponents, okay? Alright, we are back to our last question. I will just talk about it today, and we will continue tomorrow, okay? And this is a very comprehensive question. It looks like just sketching a function, but in the background, you will pretty much review each and every chapter we have covered so far in this class and previous class. Like finding xy intercept, factoring, and finding zeros, symmetry. and behavior. That's what we did today. And behavior. All will be used, okay? Just to sketch this as perfect as possible. But it's still gonna be a rough sketch. There will be, of course, some, it's not gonna be computer specific, precise. So, but we will do hand sketch with the help of these 7 steps as good as it gets, okay? But that's tomorrow.